You're watching a Channel 98 NBISD TV production.
Oh, hi there. Welcome to another edition of Deja Vu. It's Algebra 2. I'm your host, Kevin Corpy. You're probably wondering what we're doing here. Well, today I'm with a very special assistant, my little veterinarian assistant, Tate.
Hi.
And what we're doing is we're trying to make a mixture, a protein mixture, from a beef mix that has a certain protein content and a pork mix that has a different protein content. And the goal here is to try and mix these two different feeds that have different protein contents into a protein mixture that has a very specific protein content. Now, you may wonder how that's done. Is it more than just trial and error? Put a little bit of this, a little bit of that, taste it at the end, and see if the protein level's right? Well, that's not a very tasty, nor is it very efficient method. But there is a way to do it, and guess what it involves? It involves mathematics. Mathematics that you will learn on today's episode. So if that sounds intriguing to you, download those worksheets from www.newbraunfels.txed and stay tuned for another mathematical episode of Deja Vu.
It's Algebra 2.
All right, welcome to Lesson 6 of Deja Vu. It's Algebra 2. Today we're looking at linear systems of equations. Now I know you're thinking to yourself already, oh my gosh, linear equations were hard enough. Now we're looking at systems. Oh yeah, by the way, what is a system? Well, first of all, to answer the question of why are we studying systems to begin with, systems are basically a set of equations that can be used to represent linear relationships, or in other cases, nonlinear relationships involving different constant rates. That's specific for linear. So what is a system of equations? A system of equations is a set of two plus equations containing two or more variables. And in the real world, many things that have an output depend upon multiple things that are input. So it's more than one variable that control the output. So systems, we're going to look at that today. A linear system is a specific type of system that contains only linear equations. Before we continue, we need to recall what a line is and what the solution to a linear equation actually represents. So I have this equation here, y equals 2x minus 1. It has a numeric representation and a graphical representation. Well, basically, any value of x that when I plug in here gives me an equivalent y value on the left and right side is going to be a solution to the system. So these are sets of ordered pairs. Any x value that when I plug in will give me a specific y value is a solution. And if I look right here at this table of values, I have the 2 highlighted. And so if we look right there, when x is 2, if I plug it in, 2 times 2 is 4. 4 minus 1 is 3. I get my output of 3. Well, this creates an ordered pair of 2, 3. Now that ordered pair has a physical location on the graph. You go right 2 and you go up 3, and that's where this x is, and that's a single point. Well, if you look at this table of values, these are all integer values of x that when I plug in here give me these integer values of y, and these will form a set of ordered pairs that will make up part of the line. Now there are also other x values between these integers that I haven't used, but you could think of this line as being made up of an infinite number of very small dots or points that are actually ordered pairs, x values and y values, that when you plug into this equation on both sides yield a true statement. It's kind of like when you get really close to the television screen of a high-resolution TV. Your parents might tell you to get back, but when they're gone, look very closely. You will see that there are actually small pixels there, and that's what a line is made up of. The pixels would actually be the points. So what is a solution set to a system of equations? Well, a solution to a system is basically an ordered pair that satisfies not just one of the equations, but both equations in the system. So let's look at this example right here. It is a system of linear equations. Now this open brace right here is called a brace. We used it when we had set builder notation. We're using it to denote a set of equations. And for some particular reason, mathematicians have just grown lazy, perhaps, and not closing the brace on the right side, and that's okay. It's conventional just to have it open on the left. But I know these are also linear because notice it's x to the first and it's x to the first. So here's two equations. And the first thing we want to learn to do is to verify if, in fact, an ordered pair is a solution to the system. So remember, it has to satisfy not just one, but both equations. So let's take the point 2, 4. And let's go ahead and see if it's a solution to the system. I will plug it into the top equation first. So this 2 is my x, and this y value is 4. And I carefully plug in. So in the top, I get 2 minus 2 times y, which is 4. And I want to know, question mark, is that equal to negative 6? Well, I'll just work out the left side. 2 minus 8. Well, 2 minus 8 is negative 6. So is it equal to negative 6? Emphatically, yes. So it is a solution to this equation. In other words, it's a point on this graph. But is it yet a solution to the system of equations? Well, we have to plug that same ordered pair into the denominator. Or not the denominator, my bad, the bottom equation in the system. So I will plug in now an x equaling 2. So I get 2 times x, which is 2. Does that equal 8 minus my y value, which is 4? Well, 2 times 2 is 4. And 8 minus 4 is 4, so yes, again, on both counts, this ordered pair, when I plug it into both equations, gives me a true statement. So what does that mean? That means that the point 2, 4 is not just a point or an ordered pair on this graph, but it's also an ordered pair or a point on this graph. So it is graphically a common point between the two equations. I'll talk more about that in here in just a little bit. Well, let's look at this one here. I got a different ordered pair, the ordered pair 3, 2. Is it a solution to the system? Does it actually satisfy both equations simultaneously? Well, let's plug it into the top equation. And I get x, which is 3, minus 2 times y, which is 2. Does that equal negative 6? Well, let's see. 3 minus 4. Does that equal negative 6? 3 minus 4. That's negative 1. Negative 1 does not equal negative 6. So this ordered pair right here does not satisfy the top equation. So is it a solution to the system? Well, guess what? It can't be. If it has to satisfy both, and it doesn't satisfy one, then see you later, you're out of here. So, we got the one solution here. The question is, though, by verifying this one that it works, we know we have at least one, and we have found another one that doesn't work. So some of you at home might be wondering then, can a linear system have more than one solution? That's a very reasonable question. In a minute, we're going to actually try and find the solutions rather than verify them. And it's nice to know when to stop looking for solutions. If there's no more, let's go on to other math problems. Well, again, to emphasize, the graphical solution to a system is going to be an ordered pair or a point that is common between the both graphs. And if an ordered pair is common to both lines, both graphs, it's going to be their point of intersection. Very, very important. So the graphical solution, basically, to a system of equations is the point of intersection between the two graphs. Let's look at this example. We're not going to be verifying anything anymore. We're going to solve the system of equations. And what that means is we're going to find the values of x and y that when I plug in, make it a true statement on both accounts. But there's nothing to verify, so we have to seek out these values on our own. Well, let's go ahead and do this one by graphing. To do it by graphing, remember, we're looking for the point of intersection. Well, if we're going to graph these two lines, we better put them into a format that our calculator can handle. So the first thing that we're going to have to do is solve these for y. Our calculator takes equations as y equals. So if I look at the top, I'm going to do a couple of steps here. I'm going to isolate the negative 3y, and that gives me negative x minus 10. And in the denominator, I already have the y. If I bring the 2x across, it becomes negative plus 1. And the last thing I have to do is just divide the first equation through by negative 3. So I get y equals negative 1 divided by negative 3 is 1/3 x. Negative 10 divided by negative 3 is positive 10/3. And the bottom equation is already ready to go. So not only did I solve them both for x, I solved them both, I put them both in slope-intercept form. So of each of these two lines, I know the y-intercepts and I know the slopes. But now they're ready to put into the graphing calculator, which I'll show you right here. So the first step to any calculator problem is to turn it on. It's down here on the bottom left. Then we're going to go to y equals. We do that, and if you have anything in there, just go ahead and hit the clear button. Well, I'm going to go ahead and type in the first equation that I'm reading carefully from my paper. It was 1/3, so I can hit 1 divided by 3x. And then we had plus 10/3. So I can actually type it in like that. 10 divided by 3. And then I'm going to hit enter, which takes me to y2. And I'll type in negative. Now that's different from minus. The negative's down here to the left of the enter button. Negative 2x plus 1. And again, a good place to start is zoom 6. And you will see that there's the first line. And the second line will be coming in here. And notice that we're looking for the point of intersection. It appears that there's only one right there. we can estimate it from the graph. It's going to be somewhere around negative 1, 1, 2, 3, 4-ish, somewhere in there. But your calculator can do better than that. We can actually find it with the calculator's numeric functions. If we hit second trace, we go to this little menu, and notice that number 5, if you're working at home, says intersect. We want to find where the two intersect, so we can click on 5, or scroll down and hit enter. It's going to ask you two pieces of information. If you only have two curves graphed, you're okay. It's going to say, is this your first curve? And it's on one of them. It doesn't matter which one, so we'll press enter, which confirms it. It should throw you onto your second curve, and it'll ask you, is this the second curve you want? Yes, it is. Then it'll ask you to guess. So all we need to do now is scroll to where we think the intersection point is and hit the enter, and the calculator will work its numeric beauty, and it'll give you that the point of intersection is x equals negative 1, y equals 3. So that is the solution to the system. X equals negative 1, y equals 3 is the point, negative 1, 3. So we can write our solution now as negative 1, comma 3. That is the ordered pair that satisfies this equation. And again, the question comes up, is that the only one that works? Can we have more than one solution? Well, think about it. If it is the point of intersection between two lines, can I draw two lines, assuming they're distinct, that are slanted, can I draw them intersecting in more than one location? Well, try as you might, if they're two distinct lines, then you can draw them any way you want, but they're only going to intersect once if they intersect at all. So in fact, the answer is a linear system can have at most one solution. But it might have less than that. Let's think about when a set of linear equations will have less than one solution. Can you draw two lines that do not intersect, that are distinct? Well, if you remember from geometry, Euclid's parallel postulate, two lines that have the same slope will never intersect in the Euclidean plane. And that's what we're working on right here. So parallel lines will have no solution to the system. Yet they do have different equations of lines. So parallel lines, no solutions. Can we have more than one solution? Well, it's almost a trivial case. If I look at two lines, here's one line, and I look at another line that pretty much coincides with it everywhere, meaning I'm going to draw it right on the top, how many places, or at how many places do these two lines intersect? Well, every point coincides, so we would say that this has infinitely many solutions, but some would even argue that, hey, that's cheating because that's not really two lines, that's the same line. And you'd be right on that account too. But you got to be careful, because I could take a line like y equals x plus 1, and I can come up with another line that's actually the same line, and I can kind of disguise it like 2y minus 2x equals 2. It's in a different form, and all I did really was multiply this one by 2 and subtracted the x. If you try to solve this equation, you're going to get one of those identities, a truism. Every point will work. So again, if we're looking at two distinct lines, they're either going to intersect to give you one solution, or they're going to be parallel with the same slope, and you'll get no solutions. Okay, so we solved something on the graphing calculator. There's going to be some algebraic methods that we want to use as well, okay, when we don't have the calculator. And the first method that we're going to talk about today is the method of substitution. There are many algebraic methods. The first we'll look at today is substitution. And the method involves doing exactly what the name implies. We're going to substitute one equation into the other. Okay, so notice that in a system of equations we have two unknowns, x and y. And to have two unknowns, we need at least two equations to get a unique solution. So the goal by substitution is to try and solve one of your equations for a single variable, doesn't matter if it's x or y, and substitute it into the other, so that we get one equation with one unknown, which we can handle. So one equation, one unknown is good. Two unknowns requires two equations, so on and so forth. Three equations for three unknowns. Now, what variable do we solve for in which equation? You're looking for an easy variable to solve for. In the first equation, notice that we have just a plain old x, and in the second equation we have a plain old y. So you want to look for these variables that have single coefficients, or coefficients of 1. I'm going to go ahead and take my first equation and solve it for x. And to do that, all I do is I add 3y to both sides. So, oops, that's a minus 10. And so x is 3y minus 10. They're synonymous. So what I'll do now is everywhere in my second equation where I have an x, which is right here, 2 times x, I will substitute 3y minus 10, because after all, that is what x is equal to. And I like to do it in 2 steps so that my substitution goes a little more smoothly, and I put grouping symbols to take the place of x because I'm going to have to distribute here. And grouping symbols help you distribute correctly. But notice now I have one equation, and it's a function of y. There's only one variable. I can handle that. So now we're solving a little linear equation. If you distribute, you get 6y minus 20 plus y equals the numero uno. And now I will collect like terms. 6y plus y, that's about 7y's. Bring the 20 across, join parties with the 1, and you get 21 over there. Dividing through by 7, you get 21/7, which is also known as the number 3. So what we have here is we have half of our coordinate, half of our ordered pair, half of our solution. Now here's the nice thing about substitution. How do we find the coordinate, in this case the x value? Well, if you use substitution, remember that equation that we first solved for x way up here? It's already explicitly solved for the variable x that we're interested in finding. So now we just use another substitution. X equals 3 times y minus 10. But what was y? Well, we found it down here to be the numeric value of 3, and now we just simplify. We get 9 minus 10, and we get 9 minus 10 is negative 1. So there you go. I write it now as an ordered pair. My solution is negative 1, comma, 3. Okay, so substitution is a very great method, and it works again if you have values of x and y that have coefficients of 1. Well, let's look at this one right here. The other method is the linear combination, or also called the elimination method. Now, what linear combination implies is that you can add or subtract any multiple or combination of one equation to the other without changing the value of the solutions. And so what we're going to do is we're going to work with the same set of equations, and hopefully we'll get the same answer, right? Well, the goal for linear combination is to eliminate, and that's why it's sometimes called elimination. We want to eliminate one of the 2 variables. And it doesn't really matter which one we eliminate. But the goal is to try and get the coefficients of either the x's or the y's to be exactly the same or the exact opposite. If they're the same, we subtract one from the other. If they're opposite, we add them together. So what I'm going to do here is I'm going to do it a little bit differently. I'm going to go ahead and try to eliminate my y's. So what I'm going to do is I'm going to notice I have a negative 3 on the first equation. So if I multiply the second equation all the way through by a 3, that's going to give me a 3 times 1 y, or a 3y. So I'll have a negative 3y and a positive 3y. But if I do it to the left side of the equation, I've got to do it to the right. So I'm going to just rewrite the first equation. X minus 3y equals negative 10. And what I'm also going to pay very close attention to is that when I write the second equation, I have my x's lined up in a column, my y's lined up in a column, and my numbers. So when I add vertically, I'm going to have like terms stacked up. So 3 times 2 is 6x plus 3y equals 3. So now I am ready to literally add one equation to the other. And if you do that, you get 7x, negative 3y plus 3y. Those are opposites. By design, that makes a 0 pair. So they go away. And then I have negative 10 plus 3 is negative 7. Divide through by 7. You get negative 7 divided by 7 is negative 1. Well, notice that I get the same x value I got up here. And I actually found the x first this time instead of the y. That's okay. Now, how would we find the corresponding y value? Well, we aren't as lucky as substitution. We don't have an explicit equation solved for y. But I can plug it back into either one of the original 2 equations, remember, because the point is the point of intersection. So it satisfies both of them. So choose the one that's more user-friendly. I'm probably going to choose the second one. It doesn't have negatives. So I get 2 times x, which is negative 1, plus my y value equals 1. And notice there's just a single y there. So that gives me negative 2 plus y equals 1. And if I add 2 to both sides, I get y equals 3. And so I do, in fact, get the same ordered pair, negative 1, comma 3. That was the linear combination or the elimination method. You also have the substitution method. Well, that's a lot of information taken in one time. So we'll take a quick break.
But don't go away, because we'll be right back.
Now, while you're gone, ponder this question. Why did the dog not talk to its own foot? The answer when you get back.
Mom! Mom!
What?
You can't find Ichabod.
What?
You don't have to be perfect to be a perfect parent. There are thousands of teens in foster care who would love to put up with you.
Yesterday, my friends told me to smoke some pot, and I did. Then today, they said I should try and fit my fist into my mouth. It fits, but I can't get it out. I'm an idiot. I'm under the influence of others, and that ain't me. That's what he said.
Live above the influence. Above them, above weed.
Welcome back to Deja Vu. It's Algebra 2. I'm your host, Kevin Corpy, here today with...
Kate.
Did you get a chance to think about the answer to that perplexing question while you're gone? Why did the dog not speak to its own foot? Well, the answer is...
Because it's not polite to talk back to your paw. Ain't that right, Tate?
That's right, Tate.
Yay!
Yeah, back to the show. All right, now it's time for
Deja Review.
Okay, we've learned to verify solutions, we have learned to solve graphically, and we have learned to solve algebraically two ways, by substitution and linear combination. Now it's time to apply what we've learned. And here's the application. It's a real-world problem. So in this case, we are going to have to write our own equations. They're not handing us two nice equations. We have to kind of squeeze our own orange juice from these oranges. Careful reading is the first step. A veterinarian, that might be me, might be you, might be Tate, needs 60 pounds of dog food that is 15% protein. So let's say we have a special animal that needs to be on a 15% protein diet. Well, what we're going to do is we're going to combine a beef mixture that is 18% protein with a pork mixture that's 9% protein. So notice that 18% is too much, 9% is too little. So we're going to combine the perfect amount of each of them to achieve our 15% protein, and we want to make a 15% protein blend that is 60 pounds. Woo! Well, how are we going to go about doing that? Well, the first thing we need to do is define some variables. We could use x and y, but I'm going to make them very meaningful for the problem. I'm going to let b equal the amount of beef mix that I have to use, and we're going to use pounds for that unit, and I'm also going to let p be the amount of pork, and that's very reasonable, right? So we got b for beef, p for pork. Can't get those confused. Well, now we need to write an equation, and the first equation that we're going to write is going to be based on the amount that we have to have in the end. I know that the number of pounds of beef plus the number of pounds of pork that I add have to end up being my total poundage of 60, right? Well, guess what? There's one of the two equations. But I can't solve a unique solution because I have two variables in one equation. There are infinitely many values of b and p that add to 60. I want the one that's going to give me a 15% mixture. So the second equation is going to come from not the amount, but from the percentage of protein that we want. Now here's how we do percentages. Whatever we add in poundage of beef, I know that it's going to be what percent of protein? Well, the beef is 18%, so 18% as a decimal is 0.18, plus whatever I add in poundage from the pork is going to have a percentage of protein that is 9%, and as a decimal that's 0.09. So I get 0.18 times b plus 0.09 times p is going to end up equaling my 60 pounds that I want, and what's my desired protein mix on the end? 15%. So I want it to equal 0.15 percent of 60 for the protein content. Well, that's another equation. It's not very pretty. It's got decimals in it, so we're probably going to be using our calculator on this. Well, let's go ahead and write out our equation. B plus P equals 60, and 0.18B plus 0.09 P equals 0.15 times 60. What does that actually equal to? Well, your calculator will help you figure out that that is, in fact, the number 9. Okay, so we can simplify that right there and make it a little more useful. Well, how are we going to solve these? Well, we can solve it by graph. We can solve it by substitution. We can solve it by linear combinations. This is a good candidate for substitution because in the first equation I have two single variables. So I'll go ahead and solve it for b. So I get b equals 60 minus p. And now in the second equation, everywhere I have a b, I can plug in its equivalent, 60 minus p. You got to get both equations involved. So here's the second one, 0.18 times b plus 0.09 p equals 9. And again, I do like to do it in two steps, so I've left a little space here for b. And even if you have the same color, it works, but even using a different color is nice to show the substitution. So 60 minus p, 60 minus p. Now I have my equation that has one variable in it, and it's just ready for us to solve. It's one equation, one unknown. So let's do the math. Calculator if you need it. 0.18 times 60 is going to give you 10.8. And then I have minus, if I distribute, 0.18p plus 0.09p equals 9. And then I'll combine my like terms. I got my variable terms, p's, right there. And if I combine those, I get negative 0.09p. And if I bring my 10.8 to the other side, it becomes negative. Adding to the 9, I get negative 1.8. And finally, I divide through by negative 0.09, and I get 20. And that is pounds. And since it's p, that means I have to add 20 pounds of pork. Well, how much does that leave left over for the beef mixture? Well, you can probably figure it out, but if you forget, remember substitution, plug it right back into that equation. And so the amount of beef is going to be 60 minus 20, or 40 pounds. So there you go. Now you have it down to a mathematical science. You don't have to just add different varieties and test it for protein. That gets expensive. It's not very tasty to be tasting dog food either. So now we've got 40 pounds of beef, 20 pounds of pork, and we know for sure, mathematically, without a doubt, that we're going to get our 60 pounds and we're going to get one healthy dog if it needs 15% protein. So there you have it. Systems of equations. Very, very important topic of mathematics because it deals with more than one variable. And many things in the real world do involve more than one variable.
Good job.
And then we also looked at a very important application today. So hopefully that motivates you to continue practicing and learning how to use all the methods we talked about on today's show.
Good job.
But until next time, I'm Kevin Corpy,
And I'm Kate Corpy.
reminding you to do your homework. Just talk. No, you don't. You just talk.
Testing, take 3, 2, 1.
You don't
Testing.
look- You don't look at it. You don't touch it. You just. It's not even there. You just.
Testing.
I'm your host, Kevin Corpy, and I'm here today with my little handy assistant. Okay, start.
He's supposed
Yeah.
to
We'll.
say my name.
Okay. We're green. All right. What Tate doesn't know is we're actually mixing up our dinner tonight, right, Tate? Now we're coming back, and you're doing the punchline. You're gonna look at me and say, "Ain't that right, Paul?" And I'm gonna say, "That's right."
No, it's not. Ain't that right, Paul? It's,
Ain't that okay?
What was the answer again?
Okay. Why? Because it's not polite to talk back to your Paul.
Okay.
Ain't that right, Dad? That's right. And then we'll high five.